Let us see an interesting topic 2.3.2 estimation of small distances of chapter 2 units and measurement. See, when it comes to estimation of very small distances, like let us say size of molecules. Now size of molecules are of the range of 10 raised to minus 8 meter to 10 raised to minus 10 meter, which obviously we cannot measure by vernier calipers or let us say screw gauge. By screw gauge you can measure up to 10 raised to minus 5 meter only, not less than that. So for 10 raised to minus 8 meter and 10 raised to minus 10 meter and so on, we cannot use screw gauge or something like that. Even microscopes have some limitations there. For example, here an optical microscope is shown. Now this optical microscope make use of light, visible light, and this visible light is of a wavelength 4000 angstrom to 7000 angstrom, that is 4 into 10 raised to minus 7 meter to 7 into 10 raised to minus 7 meter. That means they can measure up to 10 raised to minus 7 meter because the wavelength is of the order of 10 raised to minus 7 meter. So microscopes using visible light can measure up to minimum 10 raised to minus 7 meter. That means this microscope cannot measure 10 raised to minus 8 meter to 10 raised to minus 10 meter what we are talking. Now another option is electron microscope. Here a figure is shown of electron microscope. This electron microscope uses electron beam, and this electron beam is then transformed in form of waves with very low wavelength, and that is why this electron microscope can measure up to 0.6 angstrom. That means it is 6 into 10 raised to minus 11 meter, 6 into 10 raised to minus 11 meter. So by electron microscope we can measure molecules and atoms also. Another option is tunneling microscope. Here a figure of tunneling microscope is shown. By tunneling microscope we can get a resolution of nearly 0.1 angstrom, that means 1 into 10 raised to minus 11 meter. So by this tunneling microscope you can measure up to 1 into 10 raised to minus 11 meter or something like that. That means this tunneling microscope can measure size of molecules and atoms as well. Now let us see a simple method of estimation of size of molecules, that is monomolecular layer method. See the name, monomolecular layer. Mono means one, molecular means made by molecules, a layer. So a layer made by single molecules is known as monomolecular layer method. Now what is it? Let us see. This method is used to measure molecule size of large molecules like oleic acid molecules. Oleic acid molecules are larger than other molecules. That is why oleic acid and other such type of large molecule size can be estimated, I am saying estimated, by this method, monomolecular layer method. See, oleic acid is a soapy liquid and it is having a molecular size of nearly 10 raised to minus 9 meter. So how this method is implemented to estimate the molecular size, let us see. The basic idea is to form monomolecular layer of oleic acid on water surface and find the thickness T of the layer, which in turn is approximately the diameter of the molecule itself. Now see this figure here. This figure is a cross section of this situation what we want to prepare. This is water surface and here are shown the molecules of oleic acid. Obviously it is a zoomed view to make you understand this. This is water surface on which only single molecule layer is shown of oleic acid. So, this layer is having a thickness T. At the same time, this thickness T is the diameter of the molecules of oleic acid. So, if we can measure the thickness of this layer, that is oleic acid layer, then we can come to know about the diameter of the oleic acid molecules. So, how to do this? How to prepare this layer, that is monomolecular layer? Let us see that. Here is the process. First of all, dissolve 1 centimeter cube of oleic acid in 20 centimeter cube of alcohol and make a solution 1. Then from this solution 1, again take 1 centimeter cube and dissolve it again in another 20 centimeter cube of alcohol and make another solution, that is solution 2. See this figure here. Here is 1 centimeter cube of oleic acid, which is dissolved in 20 centimeter cube of alcohol. So, this is solution 1, where the proportion of oleic acid is 1 by 20 centimeter cube. Obviously, 1 centimeter cube of oleic acid is dissolved in 20 centimeter cube of alcohol. So, the proportion of oleic acid in this solution is 1 by 20. Now, from this solution 1, take 1 centimeter cube of solution. From this, you take again 1 centimeter cube of solution and dissolve it again in another 20 centimeter cube of alcohol. So, you will get solution 2. In this solution 2, the proportion of oleic acid is 1 by 400 centimeter cube. Make this clear. Solution 1 is having a proportion of 1 by 20 centimeter cube of oleic acid, and from that again 1 centimeter cube is taken and it is dissolved in 20 centimeter cube of alcohol again. So, the final solution is having a proportion of 1 by 400 centimeter cube of oleic acid. Now what? Let us see. Now sprinkle some lycopodium powder on a water surface in a tank. In a water tank, we have to sprinkle some lycopodium powder on the surface of water. Now on this surface, put some drops of solution 2, which we have already made. The alcohol will be evaporated from the drop and the remaining oleic acid molecules will spread, creating a thin, roughly circular film or patch on the water surface. See this figure here. Here is a vessel taken in which this is a water surface on which this lycopodium powder is sprinkled. So, the whole surface initially was filled with lycopodium powder. Now we are dropping some droplets which is having alcohol and oleic acid. So, when you put that drops on the surface, you can see this type of patch will appear. Means what will happen, that the lycopodium powder will be moved away. What will happen, when we will put some droplets of the solution 2 here on the powder, so that solution will try to spread out. So when it spreads out, it removes the powder, and so you can see it easily. Why we are putting this powder? So the spreading of that solution can be seen easily. Now this is shown here. You can see after the removal of that powder, a transparent patch type of thing, or say thin layer, is formed of oleic acid. This patch will be very thin and will be almost in a circular form. So we can find out the diameter of this patch, and from that we can find out the area, because area is pi r square. So, from the diameter you can find out radius, and from that you can find out the area. Remember, we have to find out the area of this patch. Now, suppose the number of drops which we dropped on this surface were n, and every droplet was having a volume, let us say V centimeter cube. That means the total drops dropped on this water surface will be n V centimeter cube. Here, let us make one thing clear, that as soon as we put the drops of the solution 2 on water surface, alcohol will get evaporated, because the boiling point of alcohol is very low. That is why as soon as it comes in contact with water, it gets evaporated. That is why the thin film which is made now is having only oleic acid and not alcohol. So, the area what we are calculating is made by only oleic acid. Now, if we have dropped n drops on the water surface and every drop is having a volume, let us say V centimeter cube, then it is obvious that the total volume of the total droplets what we have dropped will be NV centimeter cube. Mind well, this NV centimeter cube of volume is consisting alcohol and oleic acid both, because still it is in a form of drops. But when it is dropped on the surface and when it becomes a film, at that time evaporation takes place. Now, volume of the thin film of oleic acid after alcohol gets evaporated is now 1 by 400 NV centimeter cube. As we said, the volume of total droplets is NV centimeter cube, but in every droplet the proportion of oleic acid is just 1 by 400. That is why we are saying the volume of thin film of oleic acid, now it is only oleic acid as I said. So, the volume of thin film of oleic acid is 1 by 400 into NV cube. So, the total volume of the remaining oleic acid surface, or say the thin film, is 1 by 400 NV centimeter cube. But if it is a thin film, we can consider it like a disc, and if it is a disc, then we can find out the volume by area into thickness. Suppose the thickness of this thin film is, let us say, T. If the thickness of this thin film is T and the area is A, that is why the volume of this thin film will be T into A. So, the volume will be T into A centimeter cube. So, on one hand we are having this equation of volume for the thin film, at the same time we are also having this equation of volume of that thin film. So, we can compare both of these equations. So, we can write TA is equal to 1 by 400 NV. Let me clarify, here T is the thickness of the thin film, A is the area of the thin film, N is the number of droplets what we have dropped, and V is the volume of each drop. So, from this, if we make T as a subject, you get NV upon 400 A centimeter. So, this gives us the value of T, that means the thickness of the thin film. Now, in the very beginning we have discussed that the thickness of the thin film is nothing but the diameter of the oleic acid molecules. That is why we can say, assuming that the thin film has monomolecular thickness, then the thickness becomes the size of molecular diameter. That means it is the diameter of oleic acid molecule. So, we can write diameter D is equal to NV upon 400 A. Here A is the area which we can sort out by pi r square again. So, this is the equation of estimating the diameter of oleic acid. Mind well, this is purely an estimation. Because there are many things. First of all, we are assuming that the layer will be monomolecular only. But it is possible that it will not be exactly monomolecular, and that is why the result may differ than the exact value. Moreover, when two molecules are coming close, there will be some unfilled gaps between all the molecules, as we are considering these molecules as spherical. So, there will be unfilled gaps all over there. That is why also the volume what we are calculating will not be exact. Moreover, here we have considered the molecules of oleic acid as spherical, which is not the right case. The molecules of oleic acid are not exactly spherical. That is why the values or the answers will differ. But as we said in the very beginning, this is about estimation of the size of molecules. And from this experiment, the estimated value of diameter of oleic acid comes nearly 10 raised to minus 9 meter. Now let us see example 2.5. If the size of nucleus, which is of the range of 10 raised to minus 15 meter to 10 raised to minus 14 meter, is scaled up to the tip of a sharp pin, what roughly is the size of an atom? Try to understand the question. They have said that nucleus is having a size of the range of 10 raised to minus 15 to 10 raised to minus 14 meter. Now, if it is scaled up to the size of a tip of a pin, sharp pin. See, sharp pin is also having some size. So, if the nucleus size is scaled up, means it is enlarged up to the size of a sharp pin, then the question is, what roughly is the size of atom after this scaling up? If you scale up the size of nucleus, then obviously the size of atom will also scale up. Then the question is, what roughly will be the size of atom? First of all, you might be aware of this thing, that the size of atom is of the order of 10 raised to minus 10 meter. This is not given here, you must remember this. The size of atom is of the order of 10 raised to minus 10 meter. So, the question is, if we scale up the nucleus up to the size of a pin, then what will be the scaling up of the atom itself? Here it is given that the tip of a pin is having a size of the order of 10 raised to minus 5 meter to 10 raised to minus 4 meter. Now, to understand this situation, see this figure here. This is atom inside which here is a nucleus. Now, we are scaling up the nucleus up to this big. So, obviously, the size of atom will also scale up to this big. That is very obvious. Now, as it is said that the nucleus is having a size of ranging 10 raised to minus 15 meter to 10 raised to minus 14 meter, which is scaled up to the size of tip of a pin, which is 10 raised to minus 5 meter to 10 raised to minus 4 meter. That means the scaling is of the order of 10 raised to 10. You can see here the size is 10 raised to minus 15 to 10 raised to minus 14, which is scaled up to 10 raised to minus 5 to 10 raised to minus 4. That means the scaling is of the order of 10 raised to 10. It is of the order of 10 raised to 10. That is why the same thing will happen in case of size of atom also. The size of atom will also scale up to 10 raised to 10 times. So, size of atom right now is 10 raised to minus 10 meter. So, that will be also scaled up to 10 raised to 10 times. That means it will become 1 meter. Here this is 10 raised to minus 10 meter, which is scaled up to 10 raised to 10 times, that becomes 1 meter. So, the size of atom will be scaled up to 1 meter. That is our answer.